So in class, all three sections were able to get through basic question one, which is when is a set linearly independent, or how can we use a system of equations to determine if a linear set's or a set is linearly independent or dependent. The way you do is you take a generic linear combination equaling zero and then isolate using if and only if statements to construct some system whose solution helps you solve the question. Our second question is if the span is in the set. So how do we determine if the span is in, if a vector is in the span? So here, the example we're given is with polynomials. And when working with polynomials, we're going to use the following property, that two polynomials are equal if and only if their coefficients are equal. This means that we can show equality of polynomials by matching up coefficients. Okay. So in this question, we're given three functions, f, g, and h, in the real value functions, such that, and we notice that we're given three polynomials here. And we want to determine if f is in the span of g and h. Well, f is in the span of g and h if it only exists their scalars c1 and c2 such that f of x equals cg1 plus c1g plus c2h of x. This is for all x in R. Now, why is this true? This is true because that's what we define for f to be equal to c1g plus c2h. Well, now this is true. We expand the right side, we get that f of x equals c1g of x plus c2h of x. Now, this is true if and only if 2x plus 2 equals c1 times x squared plus 1 plus c2 times x squared minus 1. This is true if and only if, and I'm going to collect like terms on both sides. Here, I notice that I don't have any x squared terms, so I'm going to look at 0x squared plus 2x plus 2, and I'm going to write x to the 0 here, is equal to c1x squared, but I'm going to collect all my x squared terms. So I'm going to get c1 plus c2 x squared plus 0x plus c1 minus c2 x to the 0. Now this is true if and only if, and here I'm using this relationship that we defined here. This is true if and only if c1 plus c2 equals 0, 2 equals 0, c1 minus c2 equals 0. And now this is true if and only if c1, c2 is a solution to the system c1 plus c2 equals 0, 0 c1 plus 0 c2 equals 2, and c1 minus c2 equals 2. And you'll notice here that this equation and this equation had to be slightly modified. But this is still an if and only if statement. And now we can conclude that our vector f is in the span if our system has at least one solution. So if our system has at least one solution, it's in the span. If our system doesn't have a solution, it's not in the span. Our final question is how can we represent a basis? By using a solution set. And the way that we can do this is we start by defining what it means to be in this set. In set builder notation, we're given an object and a constraint. So we're often given what are the objects, what are the constraints. So here we're given A equals A, B, C, D, such that A plus 2B plus 3c equals 0, and a plus b plus c equals 0. From here, we can see that A, B, C, D is in W. The matrix A, B, C, D is in W if and only if the vector A, B, C, D is a solution to the system of equations A plus 2B plus 3C plus 0D equals 0, and A plus B plus C plus 0D equals 0. And we take that constraint on our set and we can use it to build a system of equations. And we can see we're in W if and only if this solution vector, which is defined using the same variables as our matrix, is a solution to a given system. Okay? And we can use the solution set to the homogeneous system to solve a spanning set for W, which we'll explore next week. And we do this by using the following steps. We define an object in our set and the constraints. We use the conditions on the variables to construct a homogeneous system of equations. These first two steps, that's what we'd expect on the quiz this week. Given a set, you can define the object in the set and use the constraints on the variables to construct a homogeneous system, or a system where all of the constants are 0. And then from there, we solve, which we'll learn to do next week.